Welcome back, everybody. This is in this video we explored the connection between the CDF and the PDF. So let's start by setting or defining this function g of x to be the integral from negative infinity up to x of the PDF f of t dt. So small f here is the PDF of a continuous variable. Well, from calculus, the fundamental theorem of calculus tells us that that capital G is in fact an antiderivative of the PDF f here. So then we also know that the CDF is the antiderivative of the PDF as well. So that tells me that the CDF capital F is the same as the function G plus C for some constant C. So let's now figure out what is this C. Well, the fact that the limit as x goes to negative infinity of f of x is the same as the limit as x goes to negative infinity of g of x plus c, because f and g of x plus c are the same, but the limit on the left is simply 0, and on the right hand side the limit of g of x is clearly 0 because of if you look at the integral definition of g of x, and when x goes to negative infinity, this would be 0. So then we see that c has to be 0. So in other words, we see that the CDF capital F of x should be the same as the function g of x, which is this function defined by this integral. So as a result, what we find here is that the CDF function f of x is equal to the integral from negative infinity to x of the PDF f of t dt. So that's the connection between the CDF and the PDF. Now, so I want to make a couple of remarks here. So if we look at the limit, if we look at the integral from negative infinity to positive infinity of the PDF f of t dt, well, that's just the total probability. So that should be 1, but you can think of it as the limit as x goes to infinity of this integral right here, negative infinity to x of f of t dt, which is the same as the CDF capital F of x, and that limit, as we saw before, is 1. Again, that's because that's the total probability. And the second remark is the probability that x is less than or equal to b, greater than or equal to a, is the same as the probability that x is less than b minus the probability that x is less than a. Notice that here I could say this because when we have a continuous random variable, the probability that x is a fixed value is 0. So this is valid, and so this is f of b and this is f of a. So the probability that x is between a and b would be f of b minus f of a. Here the capital F is the CDF again, and then if you think about what that is, so capital F of b would be, in terms of the PDF, would be the integral from negative infinity to b of f of t dt, and the capital F of a would be the integral from negative infinity to a of f of t dt. So when we subtract, we get the integral from a to b of f of t dt. So when you subtract these two integrals here, as you can see that a is less than b here, so you're looking at the integral from negative infinity to b minus the integral from negative infinity to a. So when you subtract, you get the integral from a to b. So the probability that x is in between a and b is then given by the integral from a to b of f of t dt, where small f is the PDF. And I have already made a similar comment before, but the probability that x is between a minus epsilon over 2 and a plus epsilon over 2, that should be the same as the integral from a minus epsilon over 2 to a plus epsilon over 2 of f of x dx. And this integral is approximately the same as epsilon times f of a. All right, so I will end this video here, and in the next video we will be looking at an example. So see you then.